Hello, I'm Charlie.
And I'm Ohm. And today we'll be presenting our paper, Scalable Routing in a City-Scale Wi-Fi Network for Disaster Recovery. This is a joint work between us, James, Aaron, Channing, and Hari from MIT CSAIL. So as we've seen in recent years, the internet has become overly centralized. Now, a few cities have started to serve as critical meet points for all of our nation's networking infrastructure. Similarly, this centralization happens at all entire levels, in which a whole entire city or region's internet can be completely disconnected by a few single points of failure. And what we've seen over and over again is that these outages do happen. For instance, an undersea cable can cut off regions to a whole, can cut off internet connectivity to whole entire regions. Or all the time, a service operator will have a massive outage. And this happens due to a plethora of different reasons, from hurricanes to war and conflict to even small routine upgrades, such as Rogers, which took out all of the whole entire nationwide internet provider and actually affected Charlie here.
Yeah, this is very common software bugs.
However, what you see is that in so many of these cases, for instance, here in Hurricane Helene, users will report that even though they don't have network, they still have power. And so, because of this paradigm, our group created this idea, which we originally presented at HotNets 2024, called a decentralized fallback network, or DFN. The key idea is that we want to exploit the ubiquity of wireless networks and devices, which include technologies such as access points, smartphones, base stations, satellite connectivity, drones, in order to achieve a sort of backup network infrastructure. However, there's a few key technical challenges. Well, how do we make this scalable? How do we make applications resilient? How do we prevent security and validity? In this talk, we're going to focus on that first very topic. How do we make this scalable? And to do that, we present.
City Mesh, which is a city-scale mesh forward network where we're trying to exploit millions of Wi-Fi devices in a city to form a huge mesh network. And this is being done because most buildings these days are having Wi-Fi, so they at least have one access point in it. Then most the cities will have very dense AP deployments, and the APs are not moving quite often, so they're at fixed locations. And they have enough capacity to run our DFN applications. And we do also want to integrate mobile devices into Cinemesh, for example, smartphones, laptop, and even tablets. And what you mentioned is that the Cinemesh can also complement the other fallback mechanism like satellite, namely Starlink. And we run some feasibility analysis by varying transmission ranges of Wi-Fi devices over different cities. As we can see here, more than 99% of devices are connected at 70 meter of transmission range for cities like New York City, Sao Paulo, and Tokyo. We do see that there are nearly 20% of devices that are not connected in Boston and Washington, D.C. However, we're able to run another feasibility analysis by taking an area randomly in the city at random size and want to see how many relay nodes we need to add to get the full connectivity. And here we can see that less than 1% of the original access point is needed to be added to form this full connectivity. And City Mesh, we present a new routing primitive via buildings instead of device. This is because the wireless devices are usually inside or near buildings, since people spending 90% of their time in buildings in a day. And in City Mesh, devices only need to know their current building and also the location of their neighboring buildings. They do not need to know where they exactly is in the building. So I'm talking about the geographical positioning of the devices. They don't need to know this information. And we're expecting one-shot transmissions with no retransmissions for City Mesh. And City Mesh have the following routing steps. At first is how we're going to build a building graph from a city map. And then using the building graph, we'll show that how we're going to find a path from the source building through all the memory buildings all the way to the destination building. And we also show a conduit that improves the redundancy, and the waypoint help to compress the packet header. And combining all the techniques above, we'll show how we are able to build the routing tables for a city. And finally, we'll present some suppression techniques to reduce the number of transmissions in the protocol. So starting from the very first is the building graph. As we can see here, nearly all the buildings have wireless devices. So what we can do is to hop from the wireless device in one building to wireless device in another building. So this allows us to route at the building level, like here, instead of at the device level. And although a building cannot reach all other buildings through infinitely long hops, but we can still connect the neighbor buildings together to form a building graph. With this building graph, we can now compute a path. So we have a source building on the left and a destination building on the right. And a very naive way to do it is to traverse through the minimum number of hops, like here. However, this is very risky because travel through long hop will increase the packet loss significantly. So we come up with another path cost. We take the distance d between buildings and then we raise it to the power of k. And by controlling this hyperparameter k, if we decrease the value of k, we're prioritizing on minimizing the number of hops, like here. However, as we increase the value of k, we're prioritizing making more conservative steps between buildings and through a longer path. But this is significantly safer than the hop below, than the path below.
So then we come up with this idea of a conduit redundancy. Now, one of the issues with having a set path is that it might be that not all of the buildings along this path have access points. For instance, this red building here might not actually have an access point in it. So what we do is we provide this sort of conduit redundancy, which is a sort of geofence around our original path, which adds some sort of error. So now in this new idea, even though that there isn't an access point in this red building, there might be one in this green building, which can now transmit. And then this naturally goes along the whole entire path, which improves the chance of our packet being delivered. Then we have this idea of a waypoint compression. Now, as we start to encode these extremely long paths, what you'll see is that we now require to put every single one of these buildings into this very, very long packet header. And this is obviously not scalable and will absolutely ruin the spectrum and ruin Wi-Fi routers as our cities start to scale. So we come up with this idea of waypoint compression, where basically by using the conduit, all we have to do is specify places where the conduit changes. And so instead of specifying every single building in our packet headers, we only specify these waypoint changes. And these naturally represent the whole entire original path.
However, as we keep scaling up the city size, we'll see that even though we have those waypoints, like here, we're still putting too much waypoint in the packet header. So eventually, this is still unscalable. And what makes things even worse is that for each destination, the access point or Wi-Fi devices need to compute the entire waypoint compression, and it really burns your devices. So a solution to do it is through the routing table. So we pre-compute the routing tables in some centralized server and distribute it to every building. And when a waypoint building receives the packet, it will look up the destination, and then it will deliver it to the next waypoint, and so on. However, since every single building can be the destination, then it will potentially make our routing table very large, and it's also unscalable. And to solve this problem, we present a new gridding system. So here, we are subdividing a city into 4 parts, and we pad the prefix 0001, 10, and 11. And we keep doing this subdivision, and we keep pad the prefixes. We keep doing it until a minimum grid where we call it a cell. And suppose we have a building right here, and we're able to assign a new grid ID to the building, where the first half of the grid ID is the cell's prefixes. And the second half will be a unique identifier to identify the building, since there might be many buildings in the cell. Now with this new grading system, let's look at an example. So suppose we have this grading system, and we'll see that to go through the buildings here like 4, 5, and 6 in the same grid, it is very likely that they will share the same next waypoint here as W3. So what we can do, we can merge off them and we can combine them. So this significantly condenses our routing table to some prefixes. This is very similar to how we condense the IP routing table, and actually we can use the same technique to condense the routing table for city mesh. And then since now we're solving the packet header problem where the packet header already being constant, but if we're still looking into some conduits, let's say here, we'll see that all of the building in the conduit have to transmit, and this is too much. And we don't need all of the building to transmit to go through the conduit. So we create a delay-based suppression mechanism. So let me step through an example. Suppose the waypoint is pointing at that direction, and a building is transmitting. We'll see that there are 7 buildings who receive the transmission, but the 3 buildings on the left, they're moving further away from the waypoint. So when they receive it, they will check their building map and they will suppress the transmission. And the rest 4 buildings, they can look up the city mesh and determine how close they are to the waypoint, and they can delay for different numbers. And here, the first building that is closest to the waypoint, it will transmit first and suppress the other buildings. And the same delay-based techniques can be applied within the building at the device level. So suppose this yellow building is transmitting and we have 5 devices in it. And as we can see, there are buildings that are moving further away from the waypoints that are in red, and we have ones in green that are moving closer to waypoint. Although each device cannot tell where exactly they are in the building, but they can estimate their location by overhearing or monitoring the data packets from the other buildings. And here, node C sees 2 other buildings that can make forward progress. So it'll be rank 1, and it will transmit first and suppress the other nodes. So that significantly reduces the number of transmissions in the protocol.
So now we get into our large-scale simulation results. So we simulated 70 cities in 24 countries across its continents. Sadly, we could not simulate any penguins. Cities in our simulations range from 1K to 1.9 million devices, or 136 to 1.4 million buildings. We use building data that's released by OpenStreetMap, and we also use NS3. So first we get into our first result, which is the deliverability result. Here we just look at cities with 100K to 500K devices, so we group them together. On the x-axis here, we have drop rate, which is the average loss rate of each packet transmission. We simulate 3, which is 0.2, 0.3, and zero point 0.4. And on the y-axis here, we have our delivery rate from 0 to 100. And so basically, in each city, we send 100 packets, and I'm recording how many of those 100 packets get received. So on what you'll see here is that both Weave and GPSR don't perform very well, and in fact, barely are able to achieve 20% delivery. And as the loss rate increases, this almost degrades to nearly 0%. However, what you'll see is that CityMesh is able to achieve nearly just over 40%. Even at a higher loss rate, it's still able to achieve that still 40% rate. Similarly, if we look at the group from 500K to 2 million device cities, we'll still see a very similar trend where GPSR isn't even able to achieve an average of about 20% delivery, while CityMesh is still able to achieve nearly 40% delivery. Then if we look at the number of transmissions required to achieve that deliverability, we look at, on the x-axis here, we have the average transmissions per packet, and on the y-axis here, we have the delivery rate. Here, we're just going to look at all of the cities under 10K devices. I'll show you more in the next plot. But here, what we'll observe is that the top left here is the absolute best. And what you'll see is that CityMesh here has the lowest number of transmissions while still having the highest average delivery rate, followed by Weave, which has more transmissions, but lower delivery, but still less transmissions than GPSR, which does have a slightly higher delivery. And you'll see that this trend happens across all of the different regimes, where CityMesh tends to have the least amount of transmissions while still having a higher delivery rate. Then if we look at our routing table sizes, what you'll see is that here we show our 4 largest cities, Melbourne, Kabul, Los Angeles, and Dar es Salaam, which are nearly 1.4 million buildings. And what you'll see is that the maximum routing table size that we actually need to store is only 1,400 entries, which is only a few kilobytes of data.
We also contribute a physical testbed on MIT campus, which consists of actually more than 300 nodes. And here are some pictures of our testbeds. And we're at the end of our presentation.